So for section 9.3, we're going to be looking at means. So just basically what we did with proportions, but just with means. PRTC is very similar, but actually we're going to start with another issue first. Because we've already ran tests comparing means before. When we had groups and we had a pre-test and a post-test, what we did is we were able to actually just subtract the data and then run a test on the difference. Okay, so why can't we just do that here? Well, because we're dealing with independent samples where one population is not related to the other one, so I can't match it. I can't just say, well, this person took a pre-test and a post-test. I'm comparing two different populations. So maybe the means at two different schools or the averages of two different states, okay? So the first thing we do is just kind of try to hash out when could I do a matched pair where I basically I find the difference and then I run a sample or I run a test, a one sample test on the difference, right? Versus here, I can't find the difference because they're not really related, and so I have to run a two sample test. Okay? So, insurance adjuster is concerned about height estimates they are receiving from Jocko's garage. To see if the estimates are unreasonably high, each of 10 damaged cars is taken to Jocko's and then another garage, and the estimates are recorded. Okay? So are these two groups, this Jocko's garage and this garage, are they independent or dependent? Are they related to each other? Or are they, right? Are they related in some way where we can match them and subtract them and run a one sample test? Or are they different where I have to run a two sample test? Okay? Well, assuming we have different managers, we have different people kind of running everything here, then basically what we would do is we would not be able to match this data and we would have to run a two sample test. These two groups are independent of each other. So we would have to run a two sample test. On the next ones, safety engineer records the braking distances of two types of tires. Each randomly selected sample has 35 tires. Okay? So we have a braking distance of one type, braking distance of a second type. Are they matched? Are they the same company? Could I just match them and find the difference? In this situation, I would say two different sets, two different groups. We would need independence here, which means we would run a two sample test. Sociologist claims children's age 3 to 12 spend more time watching television in 1981 than ages 3 to 12 do today. Okay, so we're comparing children ages 3 to 12 back in 1981 versus children. So again, it's tempting that because I'm dealing with two groups that are the same age, right? But are they matched? Are they paired, right? Are they dependent? Do they affect each other? Okay. Does this group right here match to this group right here? Can I say, well, person one matches with person one, person two with person two? If they don't match, then that means these two groups are independent. We would have to do a two sample test. Notice here, SAT prep score claims to improve test scores. Data is collected on 30 students before and after. Before and after. We are matching the same person with a score before and a score after. The score before, right, if they did really well the first time, they probably did really well the second time. If they did really poorly, they probably didn't do as well, but hopefully they improved, right? If you already scored really high, you may not be able to score much higher. So these two affect each other, but we basically have a dependent relationship. We have one group that is getting a pre-test and a post-test. So what I would do is I would match the data and then do a one sample test on the difference of the data. And that's what we would have done on the previous chapters. Advertising executive claims, there's a difference in the mean household income for credit card holders of Visa and Gold, right? Two different groups, right? Do they affect each other? If you have a Visa Gold, does that mean it's going to affect somebody with a Gold MasterCard? We don't know, right? These people we can't match like person to person, so this would be independent. We have to do a 2-sample test. To study the effects of a fuel additive, gas mileage is measured on cars before and after. Before and after. We can match how did they do before the additive, how did they do after. That makes this a dependent relationship. We could match the data and run a 1-sample test on that. And last, nutritionist claims particular exercise program will help participants lose weight after 1 month. Subjects are weighed when? Before and after, matching the data. Your weight before affects your weight after. These are dependent. We could match the data and run a 1-sample test. Okay? So here's the issue. We're going to have data that can't match. So what do we do? Well, here's one of the examples. Here was the MasterCard and the Gold MasterCard and the Visa Gold, right? So this is the average income. The executive claims there's a difference in the mean household income for the credit card holders. Okay? Do the results support this claim? This doesn't tell me whether I should run a hypothesis test or a interval. So really either will do. Be careful. Like I had several people on the last test or on the last quiz. If they ran a confidence interval, right, you would have to decide if 0 is in there, there's potentially no difference. So that's really how you would do that. I'm going to go ahead and run a test. First of all, what are our parameters? Not P though, right? We're dealing with mean. The average income of which fruit group? Visa, Gold, okay, member versus the average income of a Gold MasterCard member. What are the requirements? Well, this is actually not very difficult. We've done this before. It's just now I got to do it for 2 groups. First, the results of A. So what does that mean? SRS was stated. How do I get normality? Well, in the past we said at least 30, right? Now this is kind of fun though because they're going to let a little bit of slippage on this because I'm combining 2 different sets of data. So what they'll do here is we need either normality is given, which they didn't state that, or our sample needs to be at least 15. Why 15? Because if each one has at least 15, and I combine them together, then combined they'll have at least 30. I see some books that will still leave it at 30, but I'm going to go ahead and say if each one has 15, then combined they would have 30 together. The good news is each of these is 100. So 100 is greater than or equal to 15. 100 is greater than or equal to 15. We have normality. We can run a test on that. Since we are dealing with means and sigma was not given, we will use a 2-sample t-test. Our hypotheses, just like for the hypotheses for proportions where we start they're always equal, so means, we're going to start by assuming these 2 means are equal. Alternatively, Did he say one is more, one is less? He just said he believed there was a difference. So, not equal to. We're going to use these statistics, and we should be able to run the test. Menu, statistics, tests. We are doing not a t-test, a two-sample t-test. We have statistics. What was our first mean? 16,900. Standard deviation, I think, was 2,000. 12,000. And sample size, 100. Mean 2, 60,900. What did I put there? 60,900. And I'm botching this up. Okay, 12,100. Second group, 64,300. Second standard deviation, 15,000. And also 100. A lot to fill in, and don't forget the alternative hypothesis. If you hadn't stated the hypothesis before now, this should stop you, right? So we're going to go ahead and do not equal to. What do I write down? P-value, degrees of freedom. This is crazy. There's actually a formula for this. You can look it up. It's kind of complicated. I've had professors that have showed me how to derive that formula. You don't need to mess about with all that yet. We need a p-value, we need a degrees of freedom, and I'm looking for it, we need a t. So negative 1.77. We have degrees of freedom of 188.898, so 188.9. We have a p-value of 0.078. And an alpha of what? Well, they didn't give me an alpha, did they? So how about 0.05? Based on this, the p-value is greater than alpha. So, since p-value is greater than alpha, we fail to reject the null hypothesis that the means are equal, insufficient evidence to reject. Okay? We could, just for fun and giggles, we could run a confidence interval on this. What if my test had been a two-sample t interval? Okay? Keep in mind, two-tailed test, alpha level 0.05. I'm going to do a 95% confidence interval. Menu, statistics, interval, two-sample t interval. Same numbers as before, 60,900, 12,000, what was that, 100? And 64,300. $15,000 and 100. What do I need to write down here? We need the lower and the upper. So negative 7189.24, negative 7189.24, and an upper of 389.25, which means what? I am 95% confident the, not an individual mean, the difference of the means, the mu1 minus mu2, difference of the means, is between negative 7189.24 and 389.25. How did these two say the same thing, right? Here we said, well, we think that we can't reject their equal. Here, what number is in the interval, right? If 0 is in the interval, there is potentially no difference. Up here, we weren't able to prove a difference. Here, 0 is in the interval. We think that there's potentially no difference. They say the same thing. For number 2, we have, we're just going to do a 95% confidence interval only, okay? And so when I look at this, study was conducted to see if an oral supplement helped to reduce weight. After 12 weeks, 42 subjects, so we've got the sample size. Had a mean weight loss of 3.2 kilograms, so that would be our first mean. And a standard deviation of 3.3. We've got a standard deviation. During the same period, 42 subjects, B and N2, had a mean weight loss of 4.2 and a standard deviation of 3.9. That's everything we need to do a 95% confidence interval. Okay. What is the PRTC? Real quick. P, we're dealing with means. Our first mean is we had 2 weight loss of the herbal supplement and weight loss of the placebo, right? So this would be the average weight loss with the supplement versus the average weight loss with a placebo. Okay? Requirements. Did it say anywhere how the subjects were placed? See, it did not. So we're going to put SRS is assumed. How do we get normality here, right? This is not a matter of successes and failures. What we're going to say is that each sample needs to be at least 15. So our first group, we had 42. Our second one had 42 as well. So we have normality. Our test will be a 2-sample T interval. We have a calculator for that. Menu, statistics, intervals, 2-sample T interval with statistics. Our first mean was 3.2 with a standard deviation of 3.3. So 3.2, 3.3. 3.2, 3.3, and I believe there was 42 people. Second group had, make sure I'm doing this right, 4.2 with, where did it go? 3.9. So 4.2 with 3.9. So 4.2, 3.9, and we also sampled 42 people. 95% confidence interval. What do I need to write down? Well, what was our lower and upper? Negative 2.57. Up to 0.569. Our formal conclusion, I am 95% confident that that what? Well, the difference in the weight loss is here, right? That the difference in the means is between negative 2.57 and positive 0.569 pounds. Sorry, kilograms. So what does this mean? Well, our interval went from negative to positive. There is potentially no difference. Quit spending your money on an herbal supplement, right? It ain't doing it for you. It's not making a significant difference here. Experiment was conducted to test the effects of alcohol. Errors are recorded. Okay, 95% confidence interval, the difference between the two population means. Okay, so U1, average number of errors in our first group, ethanol and placebo, right? So average errors in the drunk people are the ones that took the ethanol, so they should have filled the effects of the alcohol, versus the average effects or errors in people having a placebo. So they had something that tasted like alcohol, but it didn't have any of the benefits or fun or, I guess, dangers, right? R, what are the requirements? Well, did it say? I don't think it did, so we'll put SRS must be assumed. And how do we have normality? Well, 22 is greater than 15, and that was the 22 is greater than 15. I know it seems weird to state it twice, but basically we're saying that each one is greater than or equal to 15. My test will be a 95% confidence interval, so that would be a 2-sample T interval. Two-sample T, let's go back to intervals, 2-sample T interval with statistics. Our first mean, what are we looking at? 4.2, 2.2. So 4.2, 2.2, and 22 people. Our second group, 1.71, 1.72, 1.71. 0.72, I don't think that's right. Let me double check. 0.72 is right. Okay. And sample size of 22. So let's see how we did. 1.47 to 3.51. Formal conclusion, I am, what do we say, 95% confident that the difference in the errors made was between 1.47 and 3.51. What does this mean? Well, 0 is not in our interval. There is a difference. I would take this a step further and say it's not just that there's a difference, but the fact that it's positive implies the people who had alcohol in their system had more errors, right? No brainer. Don't drink and drive. You want to drink? Don't drive. Restaurant Associate says that households in the U.S. headed by people under age 25 spend less on food. Okay. The mean amount spent by 30 households the sample size, is, and there's a mean, with a standard deviation of, pull out the pieces. Mean amount spent by 30 homes is 2136, and standard deviation. With those pieces, can we support the claim that the first group spent less? What are our two groups? PRTC is going to be the average money spent on food outside, so eating out, for, what is that, people under 25? Versus the average money spent eating out for older people. People 55 to 64 years old. What are our requirements? Well, it says the data must be collected. Did it say randomly anywhere? I'm not seeing it jump out, so we will have to assume it. How do we get normality? Well, each of these (30 and 30) are both greater than 15. We have normality. Let's run a test. A 2 sample t-test. Since I'm doing a test, we should probably state some hypotheses. So our null hypothesis are that the means are always equal. That's the null hypothesis. Alternatively, we think that younger people spend less than the older people. Okay? Can you support this at a alpha of 0.01? Let's see. So, menu, statistics, test, a 2 sample t-test. Our first mean was what? 1526 and 225. 1526, 225. How many people? 30. Our second mean, 2136. Standard deviation, 350. And also 30 people. Okay. Be careful, make sure that we change the alternative, because we're trying to prove that the younger people spend less. What is pooled? Short answer is nothing we're going to use, so don't worry about it. But basically, pooled is if we believe that the two populations have an equal variance, that we're pulling from the same population, that they're going to be comparable groups and they would have the same standard deviation or variance. We don't know that. We very rarely know that, so you don't need to worry about using pooled. Believe that is no. Okay? Hopefully okay. Hit okay. What do we need to write down? T, negative 8.03. Alpha, we have a p-value of a lot of zeros. This is not a p-value of 8.045. Remember, e negative 11 means times 10 to the negative 11. So if you want to, you can put point and move the decimal back. Or feel free to just go approximately 0. Okay. We also need degrees of freedom since we did AT test. So how about 49.47? Based on this, you should be able to write a conclusion. Since p-value was at p was low, right? Less than the alpha. We reject that the means are equal, a null hypothesis, and conclude young people spend way less. Kind of blows your mind. You think the old people stay home and cook and all that, but I always have a student say, well, yeah, but the young people are poor. They don't have money to go out to eat. So it's not that they don't want to. The older people, they have their savings, so they go out to eat. Younger people, I guess they're poor. I don't know. Anyway, so that's it for these tests. So keep it up, and we should be doing well.